Department of ECE, R.M.D. Engineering College, and my own behalf. I welcome you all for the session 2 of Day 4, AICT sponsored faculty development program on next gen VLSI in semiconductor systems, integrating machine learning for intelligent design automation. So the session is going to be shared by the eminent speaker, Mr. Venu Madhav, Field Application Engineer, CoreEL Technologies Private Limited, Bangalore. The topic: low power and high performance VLSI design for AI application. Welcome you, sir. I
Thank you, ma'am.
I invite Ms. Srinidhi to introduce the chief guest. Over to Srinidhi.
Evening, everyone. It's my pleasure to introduce Mr. Venu Madhav, who is currently working as a field application engineer at CoreEL Technologies Private Limited, Bengaluru, with over 3 years of professional experience in the semiconductor domain. Mr. Venu Madhav specializes in FPGA and ASIC design with a hands-on expertise in programming languages such as VHDL, Verilog, and embedded C, C++, and is proficient in both Windows and Linux. His technical skill set includes working with FPGA tools like Vivado Design Suite, which covers IT integrated, Vivado Simulator, Logic Analyzer, and he is also well versed in mental graphics and asset design tools such as Tanner, Nitro, RTL Precision, and Leonardo Spectrum. As a part of Core EL University program team, Mr. Reno has been instrumental in bridging the gap between the academics and industry by conducting many numerous workshops and training sessions on topics such as FPGA design flow, embedded system design on Zinc 7000 SoC, and PYNQ Python productivity, AI ML applications using FPGAs and ASIC design methodologies. With a strong technical foundation and dedication to knowledge sharing, Mr. Venu continues to empower students and professionals in understanding advanced design flows for modern AI driven systems. Please join me in warmly welcoming Mr. Venu Madhav sir to deliver his talk on low power and high performance VLSI design for AI application. We welcome you, sir. The session is over to you. Thank you, sir.
Thank you. Thank you so much for that introduction. And I'd like to welcome all the participants again to the session. So today we're going to discuss about low power and high performance designs using the current day tools, right? So let me just share my screen. I'll please start. Yeah. I hope my screen is visible to all of you.
Yes, sir. It's visible.
Perfect. Right. So again, we are here to discuss about the low power, high performance VLSI designs for AI applications. We'll be going through a process here where we'll not only be concentrating on AI applications, but a myriad of applications per se. So before we start off the session, we need to have an understanding of how we are able to achieve the low power consumption and high performance within our devices. Either it can be for prototyping or it can also be for implementation, right? So FPGAs are more efficient for prototyping, as many of you might already know, and we're going to look at the performance indicators and performance modifications that will help us to achieve the targets, right? So in today's session, we're going to understand what is the architecture of the FPGAs and how do they help us to implement our designs, whether it be high performance programming or whether it be high performance computing, DSP modules, and there are many other such things. Okay, so we'll also look at how the design flow affects our output altogether, mainly concentrating on how do we understand our designs at a very ground level. Okay, then we're going to understand how we can observe the power and performance reports along with what is embedded system designing, and finally we're going to land upon the Python productivity, right? So I've chosen this particular flow for the session because this encapsulates the whole FPGA designing and an extended version of the productive design flows. Okay. So when we talk about FPGAs, the modern day FPGAs are going to be from Xilinx specifically, they are called the 7 series architecture FPGAs. Okay, Xilinx 7 series FPGAs. So what we have when we are talking specifically about FPGAs is going to be logic resources, a large number of logic resources that will help us to run our designs either for testing, either for design analysis. It can also be for all the way to prototyping and deciding what is happening with our algorithms. Okay, so the logic resources are the most important thing when we're talking about the FPGAs. So when we talk about logic resources, we have something called as slices. These slices are what contains multiple logic resources, whether it be your LUTs, whether it be your multiplexes, your carry chains, your flip-flops, right? All of these are available within your CLB, and this is the most important block when we're talking about any FPGAs, right? Not only that, but we can also find a lot of other resources available to us as well, whether it be memories, whether it be clock distribution units, management tiles, right? So if we slice open an FPGA, we'll be able to see a structure, something similar to this. Okay, so at the core we have our CLBs, the large number of CLBs to be precise. So CLBs again are configurable logic blocks where we'll be able to place our logic. And we also have dedicated memory units, IOs, the management tiles, right? They can be clock management tiles, they can be general management tiles, right? So there are multiple such things. And when in with respect to today's flow that we are discussing about today's topic, when we talk about low power and high performance computation in VLSI, this is where the FPGA, the modern FPGAs or FPGAs today shines a lot, is has dedicated resources for complicated tasks, right? So you can technically go ahead and design your own DSP, implement it using CLBs on an FPGA, and you can achieve your results. You can implement that and understand what is happening within your design, how is it performing. You can take out all those reports. We're going to look at all of this with a demonstration, but just for our understanding, this is possible, right? But when we talk about FPGAs in general, or when we are trying to implement high-end algorithms, whether it be any kind of neural networks or machine learning algorithms or AI algorithms, what we see is that instead of investing the available resources, all the available resources for menial tasks, FPGAs in the modern day are designed in such a way that we have dedicated resources. As we can see, we not only have CLBs, but we have dedicated block RAMs, dedicated distributed RAMs. We also have something, depending on the architecture, we can also find ultra RAMs and high-speed memory units as well, right? So similarly, when we talk about FPGAs or VLSI in general, we'll be able to see dedicated resources for dedicated tasks. So what do we mean by that? Even in the basic 7 series architecture that is running today, we'll be able to see built-in DSP blocks, built-in FIFO logics, built-in buffers. Okay, all of these are helping us to uh, diversify the utilization of the resources. Okay, so by diversifying the utilization of resources, we are able to achieve much better throughputs when compared to running our designs barely on the CLBs or trying to completely depend on the CLBs itself, right? So there are multiple variations, multiple flavors, if you may, when we're talking about the Xilinx AMD FPGAs. Okay, so what do we have for offer is we have multiple families within the 7 series architecture that can help you with different orientations when you're working, right? So you have your Spartan series chips, you have your Atix, you have your Kentix, and your Vertex chips, right? So Each of these families are meant for a specific application, right? They have their own specific capabilities for your applications. So when we talk about the Arctic 7 chip, it's a low power, low cost device, right? That can be used for our applications. So when we talk about Arctics, we are looking at a lower end logic resources available to us. Okay. So when we talk about the resources, we have for Arctics, we are looking at somewhere between 20K and 355K resources, where you have limited amount of RAM and DSP slices, and your transceiver performance is somewhere under 5 gigabits, right? So essentially, it's around 3.75 gigabits. Yeah, and you have a low IO count, and you will be using slightly higher voltage compared to other families. At the other end of the spectrum, you have Kintex and Vertex chips, where you will be able to see much higher number of logic resources. Not only that, you will also be able to see much higher end RAMs also, the memory blocks as well. Okay, but when we talk about the where do we use Kintex and Vertex chips? It's about the computational power that comes within the FPGA itself, right? So when we talk about the computational power, what we have here is the DSP blocks, where there are in thousands, compared to the Arctic chip, where you have about 500, 200 to 500 or 700 DSP performance modules. Rather in Kintex, you have about 2000 to start with, right? And this is only one architecture that we are talking about. Okay, this is only one architecture that we're talking about. Moving up from there, you also have multiple architectures, like you have your ultrascale plus, ultrascale plus MPSoC, and then you also have something called as VLSI. Okay, so why do we have so much of distribution? Is for us to easily distribute our workloads across different performance levels. Okay, so we'll try to understand that a little bit later, but just for your information, that we can distribute the workload within the chip itself rather than going for a multiple blocks within our design. We can have all of those rather than separately. We can have all of those within one device itself, right? That is what is the flexibility that FPGA gives when we're talking about high performance and low power utilization. So an extension to the pure FPGA architecture is going to be our SoC based designing. So SoC based designing is nothing but when we have a programmable logic, which is a PL, which is a pure FPGA, the logic blocks, embedded within ARM-based chip for AMD Xilinx chips, with mostly talking about ARM-based chips, right? So you have a processing system which is ARM-based embedded along with your logic resources. Okay, this gives you the flexibility to even more control over your designs, right? So how are we going to implement this design more efficiently is being taken care by your ARM, right? So there are dedicated protocols that are available to us using the tools and the boards, right? Both in combination with the software and the hardware, you have dedicated flows that you can follow, and that is how you are able to achieve the highest performance possible. Going back to the previous slide, when we talk about Arctex, Kintex, and Vertex, pattern Arctex, Kintex, and Vertex, you'll be able to see the differentiation between the transceiver speeds and the performance outputs. Okay, so when we talk about Spartan and Arctex, you have low IO count, which are using high voltages. Okay, but when we talk about the Vertex chips, you have a much larger number of IO pins with low voltage specifications, right? So yeah, moving forward, when we talk about the Zinc family, right, the combination of your processing system along with your programmable logic, PS and PL combination, what we're going to see is a multi-core processor along with a tight integration with your programmable logic, right? So this combination is what enables us for high performance designs to be run smoothly on for deployment and understanding, right? So when we talk about the 7 series architecture, specifically the Zinc architecture, which is the SoC system on chip, we have a multi-core processor available to us on the chip, along with the programmable logic with a tight integration between these two using something called as the AXI protocol. Okay, so using this, we are able to achieve the dynamic performance that an FPGA can offer. Not only the Zinc 7000, there are multiple architectures like this. So one among this is going to be your Zinc. You have your pure FPGA, then you have your Zinc, and then you have your Zinc MPSoC. So the MPSoC stands for multi-processor system on chip, where when we talk about the Zinc chip, the processing system is for the most part a dual core processor, but you can improve that processor to have multiple cores. So what we can actually observe is that when we talk about MPSoC or higher versions of the AMD Xilinx FPGAs, we'll be looking at multi-core processors where you have quad-core APUs, dual-core RPUs, and a dedicated GPU available to you on the board itself, right? So combining all of this, right? Combining all of this will give you that flexibility to work on your designs inside one singular chip, right? And having that flexibility is what enables us to perform high-end applications that require the highest level of performance while keeping our power low, right? So there are custom protocols that our FPGAs follow, and that is how we'll be able to keep the power down and the performance high. So when we talk about the design of any algorithm, okay, when you're trying to implement something onto an FPGA, right? So we have multiple flows that we can follow. Okay, it's not a one straightforward flow. Depending on your requirement, depending on what you're flexible with, you have multiple ways to program an FPGA and deploy your algorithms. Okay, so we can, if we are dedicatedly working on only hardware programmability, we can use Vivado, and we have a combination of other tools as well. Okay, in the Vivado design suite itself, we have something called as Vitus IDE, which is a software development tool, and then we have something called as Petal Linux, that is also a part of the package. So where you can design your own OS for your algorithms to run. Okay, and an extension to that is going to be HLS, which is high level synthesis, that can be used for design as well. If you are interested more on the algorithm part rather than the customization of your design, or you are interested in deploying a design purely based on algorithm, and you're okay to let the tool take the first bite at the optimization, you can do that, and then you can intervene with the optimization yourself as well. Okay, not only that, but you can also start working with your MATLAB and other tools where you can design the hardware and get it into your design flow, Vivado and Vitus design flow, and you can carry your designs forward. Okay, so we'll go through the flow. We'll try to understand what Vivado has to offer when we're talking about the performance and the power ratios. So before we do that, I want to also talk about other architectures. Okay. So we, as I've already told you, we have multiple architectures. We have your 7 series architecture. We have your ultra scale plus MPSoC, RFSoC, right? So this is a small introduction to what kind of architectures are available to us in the market. right? You have the normal zinc chip, which is going to be a programmable logic and a dual core processing system. And then you have your ultra scale plus MPSoC, where ultra scale plus architecture, and inside the ultra scale plus architecture you have two different families, wherein you have your MPSoC, which is multi-process system on chip, and your RFSoC, which is going to be your radio frequency based system on chip as well. Okay, so depending on your requirement, depending on your design abilities, okay, you'll be able to decide from various architectures. So when we talk about ultra scale plus MPSoC, you have a dedicated resources, right? Whether it be the processing system, where you have a quad core APU, your dual core RPU, and you have your dedicated processing graphics processing units, right? And then you have your RFSoC, where you have a dedicated ADCs and DACs for your analog signal communications, right? So you have various architectures available at your disposal. And the most recent and the most high end of all of the architectures from AMD is going to be AMD Versal. Okay. So when we talk specifically about Versal, it is going to be a flexible, scalable, and performance oriented system. Okay. Why do we, how do we understand this? Is when we talk about Versal, the architecture is the highest level, and you have something called as engines for various purposes. Okay, similar to how we had dedicated resources in the 7 series architecture, where you have your pure FPGA, wherein you have your CLBs, your logic blocks, and then you have your dedicated resources like memory blocks and your DSPs. Similar to that, we also have we have something called as engines when it comes to Versal cap devices. Okay, so what do we mean by engines? There are three different engines when it comes to Versal cap. Right, one is going to be a scalar engine, one is going to be our adaptable engines, and the third is going to be your intelligent engines. Different engines, the whole we can imagine that within our chip, where we're working on three different things. Okay, so your adaptable engines at the core is nothing but your essential FPGA part itself. So these are used for your future proofing of new algorithms, support for common standards. If you want to implement your designs directly using the logic resources, you can do that. Then you have your scalar engines, which are mostly taking care of your management, your processing, your controllers. All these are going to be your scalar engines. And then you have your intelligence engines, where you're mostly working on the high computational parts of your algorithms. Okay, so you have customized memory hierarchies for all of these engines, in general what we call as engines. And we also have something called as NOC within the chip to move your data around, right? So what is happening here is, when you have the three different engines, so you have your scalar engines, that is going to be your processor and management units, engines, which is essentially your FPGA. Is you have your FPGA, and then you have some dedicated resources like memories and DSPs and file logics and all these implementation units, right? So when we talk about Versal, all these are split and kept separately. So voltage scaling, the hello. Hello.
Yes, sir.
Ma'am, I'm so sorry. I got cut off in the
No
middle.
issues. No issues, sir.
Am I audible now? Am I audible now?
Yeah, it's visible, sir.
Yeah, right. So, going back a couple of minutes. So, you have three separate divisions when we talk about the vessel architecture, right? Similar to how we used to work on 7 series and ultra scale architectures. But right now, what is happening is we'll be able to see a clear separation between their different engines. So when we talk about engines, we have three different engines. One is going to be a scalar engine, one is going to be a adaptable engine, and one is going to be a intelligence engine, right? So what are these three engines and why do we have them separately? Let's start off with the scalar engines. So scalar engines are nothing but your processors, your management tiles, and your overall controllers, right? And then you have your adaptable engines, that is going to be your FPGA and your logic resources, where you can change the way these uh, individual components work, right? They're customized. So that is why they are called adaptable engines. And last but not least, we have our intelligence engines, where these are meant for the high computation of your data. So again, we have three separate segments: the scalar engines, the adaptable engines, and the intelligence engines. So the adaptable engines, the advantage of using the versatile adaptable engines is going to be the compute density, one, and the voltage scaling when it comes to the adaptable engines. And second, going to be our scalar engines. The scalar engines are going to be essentially our processors, right? The processor, whether it be the real-time processor, whether it be the APUs, whether it be the platform management controllers. So all the control units are put into one place. That is your scalar engines. And last but not least, we have our intelligence engines, right? So the intelligent engines are going to be your AI engines and DSP engines, right? So these engines are what essentially being used for your high compute densities, right? High data rate computation is happening on your AI and DSP engines. Along with that, you also have something called as a programmable NOC, right? So earlier we used to have everything in one place. Now we are trying to split everything into separate modules, right? What we're calling as engines. Why do we do that, and why is it necessary, and how does it help us? So to understand that, when we are working with the 7 series architecture or ultra scale architecture, we also had these divisions, right? But these divisions were based on the regions, right? The area of FPGA or the area on the chip that we are trying to use, right? And what that essentially did is, and how it actually worked is based on the clock distribution. So we were talking about, yeah, let me go back here. Yeah. So we were talking about the management tiles and the clock management tiles, right? So this is how our FPGA was split into multiple regions. Rather than using the complete area of our FPGA, we are trying to decide on clocks, right? That was efficient for the most part. But if, let's say, I only have some kind of a signal processing requirement, a high-end signal processing requirement is all I'm looking for, right? So essentially what you can do is you can use the DSP blocks alone rather than disturbing or using the FPGA. Okay, so that was an issue when we're trying to use the DSPs in a certain region or in a certain area or using a certain clock. The whole region had to be powered, right? The whole region had to be powered up, and that was posing the problem when we talk about specifically the low power consumption. So splitting that up, okay, splitting that up is going to solve the issue. How is that? If, let's say, I am trying to dump a workload, okay, I'm trying to dump a workload of, let's say, an AI module, okay, so I'm trying to run a complete neural network and I have an algorithm, AI algorithm based on it, right? So my FPGA can use AI engines to do that. Okay, if, let's say, I have a lot of computation there and I feel like I can use the FPGA or the Versal chip much more efficiently, I can dump the signal processing part, okay, the DSP workloads onto the DSP engines, right? So instead of going for one and done solution, you're trying to specify specific tasks. You are going to split those tasks for different units to work on, right? So your AI engines will be dumping the additional loads that it is taking from the for DSPs onto DSP engine, and your DSP engines and AI engines together, if there is some kind of faster computation that is required, okay, it can dump it onto the FPGA. Okay, so this distribution gives you a lot more flexibility, a lot more efficiency, a lot more performance, and also a lot less power consumption if you can manage that, right? If and when we can manage the you will be able to see something called as a platform management controller here, right? Within the virtual architecture, this is available. So this platform management controller is going to help you out with reducing your power consumption overall, right? So that is how we are able to achieve high performance and low power. And to use this particular structure much more efficiently and much more time sensitively, we have something called as a programmable NOC. The programmable NOC is nothing but a network on chip, right? So having this, you're getting a bandwidth of about 10 gigabits per second, right? So that high efficiency is what gives you the freedom, gives your data the mobility that it requires from one engine to the other, one location to the other. Okay, already the 7 series architecture is much more efficient, but this is tenfold compared to that. Okay, but the workloads that it can handle are also similarly heavy. So for that reason alone, we'll be using something called as programmable NOC, which is network on chip. This can transmit data within the chip with more throughput and more bandwidth, right? And along with that, we also have other resources like our PCIe Gen 5 resources, okay, which can help you achieve the coherency that is required, the cache coherency that is required, and the DMA bandwidths that are required for these high computation algorithms. Then we have dedicated memories. You have your DDR4 memory, that gives you the maximum efficiency when we're working with memories. So back in 7 series architecture, what we have seen is that we are using dedicated RAMs, which are block RAMs, and distributed RAMs, which is also called as the DRAM. And an extension over that was using ultra RAMs, which are meant for high-speed applications, high-speed data storage applications. Then we had also DDR memories in some ultra scale ports. But here you have dedicated DDR4 memories at your disposal. And then you have your protocol engines, either your 400G and 800G core protocol engines, and they can be used for the power optimization within your chip, right? So these are the most efficient protocol engines available in the market for your power consumption, right? Then you have your programmable IOs, the input output resources, right? And also we have the transceiver leads. So the transceiver leads that are available in the Versal architecture are industry leaders as we speak. So all the way from 25 gigabits to 112 gigabits is what is the transceiver capabilities that are available to us on the Versal chip. Anywhere in the market you see it's around 50 gigabits or 40 gigabits to 60 gigabits. Okay, but in a Versal chip you have the ability to go up to 112 gigabit speeds. Okay, so that gives you the edge and the future proofing that is required for you and for your designs. So the scalar engines, as I've told you, are the processors and the controllers that are available to you on the chip, and these are mostly used for your complex algorithms. Okay, your complex algorithms and decision making. Okay, and they provide the safety for your processing and redundancy for your applications. Okay, and they help manage the complete platform, which is the Versal ECAP device itself. Okay, so the load distribution, the processing distribution, all of that is happening through your scalar engines, and you have the capability to monitor the status of your individual processes as well within your platform management controller. Okay, and then you have your application processing unit, which for this case, for the Versal chips, we're talking about dual core ARM Cortex A72 processor, which can go up to 1.7 gigahertz of speed. And the thread count and the performance is doubled with an ARM V8 architecture. Okay, so you can work on both your Linux OS or your bare metal applications as well. Then you have your CPU, which is going to be your ARM Cortex R5F real-time processing unit or real-time processing engine. And this will help you for your real-time data, real-time data or real-time controls that are required for your applications. And this also provides a low latency for our designs, the RPU. Then you have the PMC, which is a platform management controller, which is taking care of the complete chip, right? All the way from your device configurations, how you want to boot your device, where you want to put your algorithm, where you want whether you're working in the PL or AI engines or DSP engines, all of that configuration along with your the device security, device integrity, your authentication. Okay, all of these is taken care by the PMC as well. Along with that, you also have two more features where you can be working on the testing and debugging and also system monitoring, right? As PMC is doing the boot and also the distribution of your algorithms and the workloads, it can also do the monitoring of said distributions, right? Then you have your adaptable engines. Again, these are your FPGA blocks that are available to you, and The advantage of using these is the parallel processing, the data aggregation, and the sensor fusions that are possible with your FPGAs. Okay, so there are dedicated memory hierarchies for each of your engines, whether it be your scalar, your adaptable, or your intelligence engines. There are hierarchies available to you, right? And that extension can also go into the HBMs, which is high bandwidth memories. So depending on where you require these memories and how much and how fast do you need these memories, the assignment can happen using the management controller. Okay. Then we have your intelligence engines, where you have two different things. One is going to be your AI engines, and second is going to be your DSP engines. Okay. So we all know that AI is, we are trying to integrate AI into everything possible, right? Instead of the human intervention, we're trying to go for AI intervention, right? So whether it be your wireless communication, your automotive, your consumer markets, the self checkouts, the ADAS features that we have on the modern cars, okay, a lot of things are happening with AI. And when we talk about the AI engines or the intelligence engines, right? So we have our AI engines that will help us for high throughput, low latency designs, and they are much more power efficient within the vessel architecture. Okay, so these engines are ideal for AI deployment and AI signal process, AI-based signal processing. Along with that, we also have our DSP engines that are high precision with floating point computation support. Okay, so whenever your AI has the necessity for additional workloads to be taken care, you will be able to diversify your algorithm between your AI engines and DSP engines. If you need further more diversification, you can go on to the FPGAs as well. And once you are in the FPGA, you have the parallel processing that gives you unmatched performance from any other processors, right? So the AI engines that we're talking about right now are the array of VLIW and SIMD processors that can run up to more than 1 gigahertz speed. Okay, so it is much more easier and flexible for your machine learning algorithms to be deployed onto your AI engines and your DSP engines. Okay, so there are massive arrays of interconnected AI engine cores that uh, so we call them tiles, and they are scalable from tens to hundreds of thousands of tiles can be used simultaneously, and they come with their own specific set of memories, so that you don't have to store the data farther away. So you have a dedicated memory for every single tile of the AI engine, so that your processing is much faster compared to any other regular processors. That is how you get the maximum efficiency for AI and DSP deployments. Moving on, we have the NOC, as I've told you, which is programmable NOC is nothing but your network on chip, right? So this particular NOC is helping you to achieve much greater throughputs through the bandwidth that it offers, right? More than 10 Gbps, more than 10 Gbps of speeds can be achieved within the chip. And then you have your transceivers that can work all the way from 25 Gbps all the way up to 112 Gbps. So both your transceiver speeds and your on-chip speeds are much more developed when we talk about our versal chips. And then you have your adaptable memory hierarchies. So you have multiple dedicated memory modules within your chip, right? So they vary in the density and the bandwidth that they can work with. Okay, you have your local memories in your AI engines. As I've told you, each and every AI tile has its own dedicated local memory that it can use, and you have your LUT RAMs, you have your block RAMs, you have your ultra RAMs, you have your accelerated memory, which is nothing but your scalar engine memories, and then you have your HBMs that are going to be your high bandwidth memory, which are packaged along with your DRAMs. Okay, and then you have your dedicated memories, which are DDR memories, the external memories. It can be DDR4 or LPDDR that can give you high rate of storage, right? So when we talk about the speed and the density that it has, okay, the local memories are low in number but highly efficient. They're highly efficient and they are placed right next to your AI engines, coming all the way down to your DDR4 memory, which is going to be your external memory or an external memory module to be specific. Those are your high density memories. You have larger memory size, but the bandwidth is slow, right? So in virtual, we have multiple multiple families again. So similar to our Artex, Kentex, Vertex, right? So inside Versal, we have Versal AI RF, Versal AI Core, Versal AI Edge, HBM, Premium, and Prime series, right? So, okay. So what we're going to let me continue this a little further. So, similar to what we have seen in the 7 series architecture, we're going to see a lot better performance when it comes to our Versal architectures. Okay, so the whether it be the LUTs, whether it be the dedicated memories, it can be your DRAM, block RAM, ultra RAM, and accelerated RAM, and your DDR4 that is separately available, the external modules that are available to us, right? So all of those are definitely much more advanced compared to your 7 series. Okay, and we have different families for different purposes and different reasons. Okay, you have your Versal AI Prime series for your signal processing and connectivity capabilities. You have your Premium series for high-end bandwidth services. You have your HBMs for high bandwidth memory applications, heterogeneous integration of HBMs. And then you have your AI Edge and AI Core series for the low power AI applications. The AI Edge is a better option along with your real-time systems. And then you have your AI Core series that is specifically meant for your high-end AI applications. Okay. And then why do we need and what is the advantage of Versal ECAP as an architecture? Okay, so you have your CPUs, your processors, whether it be your single core or multi-core processors, where you have software programmability and flexibility with your workloads. Okay, similar thing happens to your GPUs as well. So a GPU it can have a flexible workloads depending on the distribution and the range of GPUs that are used. Okay, then comes your chips, dedicated ICs, where you have software programmability, and along with software programmability, you can have your high throughput and low latency available. And these ASIC devices are much more power efficient and resource efficient. But when it comes to ACAP, you not only have your software programmability, but you also have your hardware programmability, right? And they do have a workload flexibility, as I've given you the example of AI algorithm using AI engines, TSP engines, and also the FPGAs. So that flexibility is also available. Because of that flexibility, right, the hardware programmability and the workload flexibility, you can have a much more power efficient and resource efficient device at your disposal. Okay, and last but not the least is going to be the availability of the NOC, which is network on chip, that will give you the highest throughput in the market on any device. Okay. Let's do one thing before we move on to the lab. I want to talk to you about one more thing, which is yeah. Let me come here. So as we have discussed, there are multiple ways to program any FPGA, not just your 7 series or Versal or ultrascale. There are many ways to write your algorithms and deploy it onto your FPGA, right? So one such way of writing your application is going to be your pure hardware design flow and your embedded design flow. Okay, so when we talk about your pure hardware design flow, you're completely working with a tool called AMD Vivado, and that has a lot of features when it comes to your hardware based designs. Okay, so we're going to look at an example where we'll try to understand what are all the features of Vivado itself rather than trying to implement the design. Okay, then we actually try to implement a design using an embedded system design flow. Okay, and rather I would rather say an extension of your system design flow, right? So what we going to talk about for that is going to be your pink framework, the pink Python predictive. Okay, so what do we mean by your pink framework? You would have seen hardware where you are using the bitstream, you are designing the hardware and you are trying to dump it onto the FPGA, right? So taking that as a base layer, what we're going to do is we can create something called as kernels, or we can create some drivers. Okay, we're going to be using, rather than bare metal dumping, what we'll be doing is using Linux kernels to hold the FPGA information, the system GPIOs, the Xilinx libraries. All of these can be contained within the drivers, right? So on top of these drivers, we'll be able to run something called as APIs, which contain your Python libraries, your PL logic, your GPIOs, your interrupts, your MIOs, EMIOs, and all this. Okay. So all of this combined will give you an architecture where you can deploy the applications, right? These applications are going to be working in a Jupyter notebook, and within the Jupyter notebook, you will be able to deploy multiple Python notebooks. Okay. So what essentially is happening from the top, what we're going to do is write an application within Python, right? Using Python within the Jupyter notebook, and those notebooks are linked to your Python libraries, your DMAs and your Xilinx libraries, and those are in turn connected to your programmable logic, GPIOs, interrupts, and your overlays, right? So your drivers will be able to connect your APIs, which in turn are holding your applications, all the way down to your hardware, right? So from an application point of view, you are directly targeting your hardware, and you have the flexibility to change and retrain your algorithms, right? So the advantage of Python, most of us are already familiar with this. So Python has a large selection of libraries, all the way from NumPy, MATLAB, OpenCV, right? For any kind of applications, whether it be your defense applications, your military-oriented applications, you have wireless communication, you have your video surveillance, okay? It can be ADAS, it can be automotive, you have your machine learning algorithms and AI applications as well. All of these can be directly implemented using your Python. Okay, so let me open Vivado tool and create a new project. Let's see what are all the features that are available to us. Just a minute, let me see. Okay, let me just create it here. That is I'm just creating a new project with the thing board. Let's finish this. Right. Let me add the sources. Right. What I'm going to do now is add my constraints as well. When constraining on the time constraint. Right. So once I have this, let me open this particular design. So what we're working with in this particular design is a UART based LED using meta-hardened reset and meta-hardened buttons. Okay, we have our reset and our inputs and buttons, and we're going to run the LED based on our UART. So we are expecting some kind of a feedback from our board to our system as well. Okay. So the reason why we are looking at this project is to understand how can we customize and how can we understand what is happening with the internals of our design, whether it be the power utilization, the resource utilization, and okay, one second. Right. Okay, let me run synthesis first. Okay. But before we do this, there are, as I've told you, there are multiple protocols and multiple sequences that the Vivado tool uses, along with, in combination with, and along with your FPGA, right? Depending on which architecture you're using and which FPGA you're using, your tool will be able to decide what are all the available resources for me and how do I customize these particular resources for my usage, right? So how do we work on that? If we go to settings, we have synthesis settings and implementation settings. Okay, so where we can decide on what kind of settings do I want to apply for my particular design. Okay, so when we talk about the synthesis and implementation flows, we have multiple things that we can reshuffle and try to analyze our designs. So there is something called as strategies. Okay, we can use multiple strategies and multiple what do so this is actually called as multiple settings that we can change, right? So when we are trying to work with any of the designs, we have something called as options. Options are nothing but are dedicated flows that the tool will follow for our own customization, right? So we have multiple customizations like that. You have your hierarchy settings, you have your gated clock conversions, okay? You have your retiming, you have your extraction of your FSMs. So there are multiple settings like this to enable you to customize your design according to your requirement. So what kind of memories you want to use, what kind of how much of DSPs you want to use, or do you want to only use DSPs, and do you want to cascade all of your available resources, or do you want them to use individually? There are a lot of settings that you can go through, and there are strategies for those as well. You can change the settings here, and you will be able to customize your design for not only customizing your design, but the strategies that you will be able to follow, right? This gives you a lot more flexibility, and not only in the step of synthesis, but also in the step of implementation, right? How do you want to implement your design? Okay, so how do you want to optimize the power? How do you want to optimize your placement? How do you want to route your design? Optimization of routing, and also bitstream optimization are available to you. So depending on your requirement, you will be able to change this. This is a very important subject, because a lot of people feel like the customization that they can do for their design when they are working on creating their own designs and implementing them, they feel like they have very less flexibility when it comes to the customization. But no, you have plenty enough options for your customization. The thing is, they all are included in specific settings. Okay, so you need to be careful with this part. Okay, it's not an open customization, but it is customizing your flows. Okay, you will be able to customize your flows using your settings as well. Okay, so one thing I wanted to really discuss with you is going to be how an FPGA, or in general, how hardware is much more flexible and user friendly when it comes to implementing our designs, right? So I have a very small example that I wanna show you. So let me open the Python notebook. Okay, so when we are trying to work with an FPGA for AI or machine learning implementations, or any kind of neural network implementation and training neural networks and all these things, we have a lot more flexibility because of the added hardware programmability, right? So rather than going for software implementation or software programmability, we also have added flexibility with the hardware programmability, right? So I just want to show you an example wherein we'll be able to appreciate the difference between your pure hardware programmability and your pure software programmability and hardware programmability, right? So, this is going to be a small example wherein we're discussing about the efficiency that we have when we're using hardware compared to only software. Okay, so this is an example where I am using a binary neural network, directly dumping it on my FPGA, right? So I'm just importing the BNN, the BNN based classifiers, okay? And I already have the resources stored on the board itself, okay? So once I run the classifiers, uh, okay, so once I run the classifiers, I'll be able to appreciate what is happening within. Just a minute, I'm facing some issue. Okay, just give me a minute. So in the meantime, if anybody has any kind of questions, you can post them in the chat box. Okay, we'll try to reply to your questions and your queries. In the meantime, just give me a minute. Let me set this. So yeah, there is some installation issue within the board. So what I'm trying to do is install the Python packages, right? So yes. So once I install these packages, I'll be able to run the design without an issue. Okay, so let me check. In the meantime, does anybody have any questions? Let's share box. Okay, that's fine. Okay. Down this process, let's see. Yeah. Right. So once we have installed all the packages, um, let me open this design. Right. So again, what I'm trying to do is I'm trying to run a binary neural network, and I'm importing it first of all along with the classifiers. That's a feature called classifiers that I'm trying to implement. Okay. So these classifiers we're going to run on both the software and the hardware. So we'll do a basic comparison between our software run BNN and the hardware run BNN, and we'll try to understand how much of a difference do we face when we're working with your hardware alone and your software level. Okay. So just wait for it to run. Okay. Yeah. So restart the kernel. Okay. So the first thing is I'm trying to launch my design. I have a dedicated resources. Let me show you. So inside the folder called pictures, I have multiple images stored. This is going to be the library that I'll be pulling my data from. And from this particular library, what I'm going to do is run my design on hardware and on software, right? So let me run it on hardware and let me run it on software. Okay. So there is going to be an obvious difference between the same neural network run on the hardware and the software. So we're going to understand what it is. I'm just trying to run this design with a image that I've taken, and I'm doing a comparison using machine learning. Okay. So I'll use the classifier and try to detect the stop sign here, right? So it is running multiple detection sequences altogether, and I can run the same detection once again, where I'll be able to rectify the findings and get a clarified output, right? So my first iteration is going to find multiple locations where I have the stop sign, and the polished image is going to have the dedicated stop sign detected. But what I want you to understand here is the rate of inference and the difference of the same when you're working on hardware and software. So when I launch the same BNN neural network in real time on the software, the throughput that I'm getting, the output efficiency that I'm getting is written here, right? The classification rate is going to be 0.610 images per second, right? So the classification rate is again 0.61 images per second. Okay. And the whole inference took about 49 of 49 lakh 12,400 microseconds. Okay, comparing it with the hardware, your classification rate is improved by almost 1,000 times, more than 1,000 times, right? So the classification rate for the hardware is going to be 1,093 images per second, and inference only took us 2,743 microseconds, right? So the efficiency and the power that is consumed is going to be much larger when we're working with the hardware. And all of this is customized all of this is possible based on our hardware customization, along with the software customization and resource customization as well. Okay, so just to reiterate, so our hardware given efficiency of classification rate of 1,000 images, more than 1,000 images per second, and the software is only working at 0.61 images per second, right? So that brings us to the conclusion of how VLSI designs can be optimized both for power and also the performance using our FPGAs. If there are any questions, I'll leave the session open for questions. you can just unmute yourself and you can directly talk to me, or if you have any questions, you can post them in the chat box also. Will be available from now on. Okay. In the meantime, I'm also posting a feedback link, right? So feel free to let us know if any feedback that you want to give us. Please fill it out in the feedback form. And if you're looking for any kind of questions, queries, or anything like that, please mention the same in the feedback form. We'll try to reach out to you and we'll try to connect. Yes. Once again, thank you so much for attending this session. I thank each and every one of you for attending this session. Please let us know how you felt about the session. If you have any other questions, feel free to let us know about that as well. I'll be available both on chat, or you can unmute and talk to me directly. Thank you so much. And I hope you have a good evening. Yeah.
Participants, if you have any queries, you can unmute yourself and you can ask, or you can post it in the chat box too.
Thank you. Thank you, everyone.
Sir, if any participants ask your contact details, can I share, sir, for research purpose?
Yeah. No issues. No issues, ma'am. You can share them.
Yeah, thank you. Thank you so much, sir, for sharing your expertise among us. Now I invite Ms. Sendil Priya to propose the vote of thanks. Over to Sendil Priya.
Thank you.
Good evening, everyone. On behalf of R.M.D. Engineering College and Department of ECE, I would like to extend our heartfelt thanks to Mr. Venu Madhav, sir, Field Application Engineer at CoreEL Technology Private Limited, Bangalore, for delivering such an insightful and engaging session on low power and high performance VLSI design for AI application. Sir, your detailed explanation and live demonstration on FPGA based design workflows gave participants a clear and practical understanding of how AI driven and low power VLSI systems are implemented in the real time. So we are truly appreciated your time, effort, and your uh, passion in sharing both theoretical and hands-on knowledge, making this session an enriching learning experience for all of us, sir. Thank you once again, sir, for making this session both informative and inspiring. Thank you, sir.
Thank you so much. Thank you.
Thank you
Ma'am.
so much. I thank all the participants who have joined us for day 4 session. So let us meet in the day tomorrow in day 5 session. Thank you so much.